So let's talk about section 10.1, the fundamentals of hypothesis testing. Now understand that this is going to be a little bit long and wordy of a section, so there's a lot of words in this one, so bear with it. Please understand that when we talk about hypothesis testing, anybody in the world can make a claim about a population parameter. Now you've probably heard things similar to maybe 4 out of 5 dentists prefer Star Bright toothpaste, or less than 1% of dogs attack people that are actually unprovoked. Now, these type of things you hear quite often, and people make decisions every day based upon claims such as these. Now, sometimes those decisions are relatively insignificant, okay? Like, what type of toothpaste do you actually buy? Is it really a big deal which toothpaste you choose? Now, other times these decisions that we make are based upon these claims could be actually super important. So that's actually what the whole thing about hypothesis testing is about, is how do we actually test these claims that are made about the population parameter. And this is what this process is, hypothesis testing. It's one statistical process that claims kind of a uniform standard for actually how we evaluate these types of claims. Now, remind yourself, we've learned about this word hypothesis before. Hypothesis is a theory or premise that is often a claim that someone is making that we must actually investigate. Now, in science, a hypothesis is usually a claim about how the world may work. In statistics, however, a hypothesis involves a claim about a number value of a population parameter. Okay, now it's in reference to either it's a population mean or a population proportion or even a population variance. Now, the first step in a hypothesis test is basically you have to clearly state the research hypothesis. Now, the research hypothesis, that we actually like to call the alternative hypothesis, and we like to denote it by H sub A, okay? And make note of that because that's the actual really important part, is how we denote it and making sure kind of that information there, okay? Now, it is a mathematical statement. So when I talk about mathematical statements, these are things like greater than, less than, greater than or equal to, less than or equal to, equal sign, not equal to. Those are the types of mathematical statements. We call them inequality statements from time to time. Okay? And you're going to basically take these words and make it into a mathematical statement. Now, the other one is called a null hypothesis. Now, the null hypothesis, again, it's got its own notation. Notice it looks very, very similar, but with this one, it's called H null or H sub naught. Either way, I've heard it both directions. Now, understand that basically the alternative and the null are two hypotheses that form a pair of logically opposite possibilities. Now, throughout the hypothesis test, the null hypothesis is assumed to be true. Note that the equality must be included in the null hypothesis to establish the presumed value of the population parameter. Now, that means that basically when we look at switching from words to mathematical statements, the equal sign has to be in the null hypothesis. Now, the data then, when we collect it, hopefully will provide overwhelming evidence to contradict the null in favor of our alternative. And that's basically what we end up making our conclusions on. So hypothesis test is a technique, okay, for testing a claim about a population proportion using stat principles. Now the alternative hypothesis, again, H sub A, is a mathematical statement that describes the population parameter. Okay, it can also be called the research one. It's the one that we want to know about. The null hypothesis, also known as H null or H sub naught, is a mathematical opposite of the alternative. And again, it must always include that inequality. That's super important, guys. That's the biggest part about the null hypothesis that you want to make note of. So let's start with our first scenario here. Now, again, remember, this is going to get really, really wordy, and I'm going to look for key things that might help me with this process. So at Northwest Mississippi Community College, a syllabi for online classes states that students should expect to spend 10 hours per week doing coursework for each 3-credit-hour class. Now, the director of e-learning for the community college is concerned that students are being required to spend more than 10 hours per week doing work for each 3-credit-hour course. Now, if anything, pause for a second and see if you can see what exactly is it that we want to know. Okay, what does that director of e-learning, what are they actually concerned about? So again, that's kind of the questions that you should be asking. What are you actually looking for? What do you want to know? So the e-learning director is concerned that students are being required to spend more than 10 hours per week on the coursework than what the syllabus stated. So basically that's what we're going to look at. More than is the same thing as saying greater than. So therefore my research hypothesis is that that average, that mean, will be greater than 10. Well, what's the opposite of a greater than symbol? A less than symbol. And again, if I say greater than, the opposite should have a less than or equal to, and that will be my null hypothesis. Again, do note one of the things again that I kept saying is that the null hypothesis always is containing that equal part. Okay, and you always want to write both down. So this is why you've got the little sub A and sub 0 on it. They are literally there as a reference guide. They have nothing to do with the actual like mathematical part of it. It's literally just to notate which one's the null and which one's the alternative, because you always have two hypotheses. Okay, and again, notice that the one that has the equal to sign is always considered the null, and the one that doesn't have the equal to sign is always my alternative. Let's try this again. Now, after learning that Peter Collat of Switzerland could hold his breath for 19 minutes and 21 seconds underwater, a group of students decided to conduct a science fair project around the time an average adult can hold their breath. Now, part of the group found research that suggests adults can hold their breath for 30 seconds when submerged in lukewarm water. The other half of the group found evidence that suggests that the mean time is different if the water temperature is colder. Now, the group would like to test this claim about adults holding their breath in cold water. Again, ask yourself, what do you actually want to know? Now, what did we want to gather evidence on? Well, we want to gather evidence about investigating whether that mean time or that average amount of time that an adult can hold his breath underwater when the temperature is cold is actually different from what's reported. Okay, now they said that the reported time was 30 seconds with lukewarm water. So simply because we want to know if it's different, note that they simply are interested if it's just different from 30 seconds. I didn't say nothing about whether it's more or less. I didn't say anything about that. I just said different. So our research hypothesis is basically that that average, that mean, is not equal to 30. So therefore the opposite of a not equal is a equal. So therefore my null hypothesis is going to be equal to 30. Again, writing both of them there. And again, they should always have those alternative symbols. Let's try this again. So a leading news authority claims that the president's jobs approval rating has dropped over the past 3 months. Previous polls put the president's approval rating at a minimum of 56%. Now, the president's chief of staff is concerned about what the news reports since it is election year, and he wants to run a test on the claim. Okay, so the president's chief of staff is concerned about the news report. What did the news actually report? Well, they said that the approval rating has dropped. So we want to know, has his rating actually dropped? So since the news authority claimed that the population proportion, because we're talking about a percentage there, we're going to use P instead of mu. And again, the claim being tested is that has that approval rating dropped from that previously stated poll? Now, the previously stated poll that it was at least 56%. So if I'm going less than that, that's where we would have a less than 56% because it dropped, so it's less than. So my mathematically written alternative hypothesis would be P is less than 0.56. Again, I don't use percentages. I like to switch them out to decimals because again, we're going to be putting stuff in the calculator and we don't want percentages, we want decimals instead. Now, a logically opposite for a less than symbol will be a greater than or equal to symbol. So our two hypotheses written side by side is one's going to have the less than and the other one's going to have the greater than or equal to. And the one that has the greater than or equal to, again, the part that actually has the equal to, I don't care what it is, if it's greater or less, the part that has the equal to symbol is always then the null hypothesis. Again, lots of words. So this is the hardest part, and guys, do understand that this section here of just determining whether something is a null hypothesis or an alternative hypothesis is going to follow us for the rest of chapter 10. So make sure that you know how to identify what is the null and what is the alternative, because once we leave this section, we're going to take this another step. So the next problem says a survey of Super Bowl viewers found that 8.4% said that they were influenced to buy products from companies that advertised during the game. Now, because of rising costs, one company president has threatened the advertising team with not renewing the Super Bowl ad unless they get the results they want. He says that unless their company's ad stimulates at least 8.4% of viewers to buy the product, then they will not be airing an ad during the Super Bowl next year. Okay, first of all, as I looked through that, the first thing I saw was a percentage number. And again, it's talking about proportion of people. So I'm going to switch this to P. Okay. Now, the second thing is as I was reading through that, I also noticed, what did he actually want to know? Well, he wants to know whether or not, does this actually affect people? Is there enough evidence that the percentage of viewers persuaded to buy the company's product is too low? If it's too low, we're not going to do it. So the research hypothesis is basically, is that percentage less than 8.4%? Now again, written mathematically would be P is less than 0.084. Again, 8.4% switched to a decimal is 0.084. Well, the opposite of a less than symbol will be a greater than or equal to symbol. So my null hypothesis is that P is greater than or equal to a 0.084. Now, one thing you'll kind of notice is that no matter what, these are always the same number that's written in these two. The only thing basically different between my null and my alternative hypothesis is the symbols. So they should have the exact same numbers going between them. Now, once you've done all this work to actually put the two hypotheses together, okay, we can actually decide which of the two hypothesis data to actually support. Now, this hypothesis test comparing the merit of the two of these hypotheses, we basically have to examine the data that's actually been collected. Now, please understand, this does not actually treat the two hypotheses equally. The null hypothesis describes the currently accepted value for the population parameter, which is why that one contains the equal to. Okay. Now, the null hypothesis states kind of the status quo is that the value of the parameter is assumed to equal. Again, we are assuming here we don't have really enough evidence to say whether or not this is 100% true. So we're assuming that this is the truth. So the null hypothesis is always assumed to be true. Now, that means that the hypothesis test actually examines whether or not there's enough data that this belief of that null hypothesis is true. If there's enough data to disagree, and it has to be sufficiently enough data that the null hypothesis is not true, then we say that the null hypothesis is rejected in favor of the alternative. Okay. Now, what do we actually use? Well, that means we need a test statistic. Now, a test statistic is that value for which a decision about the null hypothesis is derived from the sample statistics that we have. Now, a sample statistic is said to be statistically significant if it is far enough away from the presumed value of the population parameter. And again, this again is we conclude that it's unlikely that the sample statistic happened to occur by chance if that null hypothesis is true. Now, the level of significance, we've actually looked at this. I just haven't given its name yet. The level of significance is denoted by what we call alpha. Alpha is basically the probability of making an error of rejecting that true null hypothesis. Okay, now again, we've actually looked at this, so this is not new. Alpha is basically 1 minus that confidence level. Now, to determine if the sample statistic is statistically significant, a confidence interval for the population has to be constructed using the methods that we found in Chapter 8, which is why we spend time learning Chapter 8. Now, the evidence is considered statistically significant when that sample statistic is so inconsistent with the null hypothesis that it's basically presumed that the value of the population parameter for that null hypothesis falls outside of that confidence interval. Now, I know that sounds really, really odd, but let me kind of maybe help you guys out with this a little bit, is that we're actually constructing confidence intervals, okay? So we did all of this stuff in Chapter 8. We actually also introduced the sample statistics. So those were those X bars and the P hats, and then S squared, which would be our sample variance squared, okay? Those are what we call point estimators, okay? Now from there, we basically constructed these confidence intervals. So we constructed, based upon the central limit theorem, that we had basically found that there was this kind of area around the mean or the population proportion, okay? We found that there was this area around here that this was basically what we have. And what we're saying is that we're determining whether X bar, my sample statistic, does X bar fall like here, or does X bar fall like in this area here inside the area that we keep it, or outside of it? So does my sample meet with my requirements that works, or does it not? Okay, and that's kind of what we're doing. Now, do understand, okay, that we actually have not actually covered the chi-squared, but please understand that you have access to those. So for my science majors, some of y'all will have chi-squared stuff. We have actually only covered this stuff that is Z's and T's, but chi-squared is also another one used, but we're not going to go too much into that one. Now, after you've actually done all this stuff and the hypothesis has been clearly stated, the second step in the hypothesis testing is basically you determine what distribution, which tells you which test statistics. So is it a Z, a T, or a chi-squared? And you also have that level of significance, okay? Now, if you're going to do this by hand, please understand that at that point, that's where you're gathering your data used to calculate the test statistic in the third step of the hypothesis test. Now, when I say gather the data, appropriate sampling techniques that we talked about in Chapter 1 would be used if you're actually gathering your own data here. For the most part, I will tell you what type of data you're already gathering. Now, the last step is actually to just draw your conclusion, and we are going to perform pretty much the calculations on the data and make that conclusion based upon what we performed. Now, there's only two conclusions that can be made. You either reject the null or you fail to reject it. Those are the only two options that you can tell me. Reject the null or fail to reject the null. Now, what do we mean by this? Well, if the test statistic calculated from the data collected basically is found to be statistically significant, then we reject the null hypothesis, okay, in favor of the alternative, meaning that there's enough evidence that says that we're outside that zone. Okay, now again, this is what I mean by this. Again, think about back to this whole normal curve that we just made, and we have, here's our confidence interval. So this is our confidence interval. Okay, basically you found some test statistic that falls out here, which means that we have enough evidence that it's far enough away from this, that test statistic, whatever it could be, it's far enough away that we can say that we reject the null. Now, this is the stronger of the two conclusions that can actually be made. Do understand, let me erase those, if it is not statistically significant, so it's not far enough away from that interval that we just found, then we say that we fail to reject it. It's actually the weaker of the two conclusions. It's not to say that we don't have enough evidence to say that the null is true. It's just we don't have enough evidence to say otherwise. Again, you're not really saying either claim is 100% true. You're just saying that there's enough evidence to go one way versus the other. And that's kind of something that a lot of people make really bad mistakes on is it's not necessarily obvious which conclusion is going to be implied, because when we run this, it's going to be a mathematical symbols. So please understand that normally you have to translate stuff into words and interpret it. So let's take a look at something that's been done and kind of see what we've got here. So in Northwest Community College, syllabi for online classes states that students should expect to spend 10 hours per week doing coursework for a 3-credit-hour class. Now, the director of e-learning for the community college is concerned that students are being required to spend more than 10 hours per work per credit hour, a 3-credit-hour course. Okay, that was the first part where we're making our claim and hypothesis. Now, we're going to conduct a hypothesis test with a 5% level of significance, and it's performed on the director's claim. Now, the result is that we reject the null hypothesis. So what actually does that mean? Does that conclusion support the director's claim? So remind yourself, again, we've already done this a little bit before. So earlier we had these were our alternative and null hypothesis. Okay? Now, remind yourself, I just said that we reject the null. Okay, so since we actually reject the null in favor of the research hypothesis, okay, so we reject the top one in favor of the second one, okay, that actually tells me that the e-learning director can be confident in their assessment that says students actually spend more time, they spend more time per week on average than what was stated in the syllabus with a 5% level of significance. Okay, it's significantly enough, a bit more than what they stated of that 10 hours per week. Again, it could be just that it's 12 hours per week. We don't know actually what the answer is. It's just significantly different that we might need to go back and do a bit more research before and maybe change our syllabi. Okay, so let's try this again. So based on a historical Board of Education, historical data for one Board of Education for a large school district, it's believed that the percentage of high school sophomores considering dropping out of high school is at least 10%. Now, high school counselor in the district claims that that percentage is too high. Now, a hypothesis test with a level of significance of 0.02 is performed on the counselor's claim, and the result was fail to reject the null hypothesis. So did the findings support the counselor's claim? Well, the first thing is we kind of got to figure out what that null and alternative hypothesis is. So the counselor claims that the percentage was too high, meaning that that dropout rate was got to be smaller than what they have, right? So it's got to be less than the assumed 10%. So my alternative hypothesis or my research hypothesis is that that proportion, P, is less than 10%. So the logical opposite of a less than must be greater than or equal to. So we have my two alternative and null hypothesis written there. And then I'm going to remind myself that since the result was basically we fail to reject the null, okay? Fail to reject the null, meaning that we fail the researcher's claim, okay? Fail to reject the null, meaning that there's not enough evidence to support the researcher's claim, that whole counselor's, that they said that it was presumed to be too high, that it had to be smaller than it. So remember that performing a hypothesis does not prove that the null is true. It just says we don't have enough evidence to say that it's not true. So there's actually 4 steps when you're doing a performing hypothesis test. State it, state the hypothesis, null and alternative. 2, determine the distribution. So you're gonna have to figure out like what type of test statistic, as well as state your level of significance. Step 3, gather your data, calculate any necessary sample statistics. And step 4, draw the conclusion and actually interpret it. Again, if we fail to reject the null hypothesis here, we cannot say that the null hypothesis is supported. What we can only say is that evidence does not support the alternative. Okay, so if you fail to reject, we just basically say that there's not enough evidence to say that it's other than the null hypothesis. We're not stating that it's true. It's important to remember that no matter what the conclusion is that neither hypothesis is actually proven to be true or not. Okay, more testing has to be done. Now, when performing these types of tests, there is actually some errors that can happen. So no matter what, there's always going to be a bit of an error. What you have are two types of errors. Is what happens if you reject a true null hypothesis. So what if the null hypothesis was actually true and you reject it? Or you fail to reject a false null hypothesis, okay? These errors are called a type 1 and type 2 error, okay? A type 1 is where you basically reject something that's already true, and type 2 is you fail to reject something that was actually false, okay? And these are the types of things that can actually happen. Now, the decision criteria that we use in the hypothesis test is we kind of really want that type 1 to be really, really small. And so the probability of committing a type 1 error, in other words, that probability of rejecting the true null hypothesis, is actually our level of significance. Whatever that level of significance is, that is that's the probability of actually having a type 1 error. Now, the level of significance that we use to draw our conclusion for the hypothesis test, yes, it is actually the same as a type 1 error probability. So normally the level of significance that we use, the smaller the level of significance, that means there's more evidence required to reject the null. Now, the most common practices in academic research is we use a 5% level of significance. That's if there is not one stated. So if one is actually stated at all, we use whatever's stated, but if there is not one, we just assume it's 5%. Many times researchers, studies, if you actually read journals, they don't provide the level of significance in their research, but they simply state what the probability of the results obtained would actually occur by chance under the assumption that the null hypothesis is true. So therefore, the reader can determine for themselves whether or not the null hypothesis should or should not be rejected based upon what alpha they want. Please understand that technically we choose our level of significance, so that is something that we choose the value of. So why wouldn't we choose a level of significance to be as low as possible? Well, there's actually a reason for that. The answer lies in the inverse relationship, which is basically if you have the probability of making a type 1 error, what's the probability of making a type 2 error? Now, the probability of a type 2 error, we like to use the Greek letter beta for. The smaller the probability of a type 1 error, the larger the probability of a type 2 error will actually occur. So if you think of it in terms of kind of a seesaw, type 1 versus type 2, which one's the worst one? Okay. I can't say which one's the worst one to actually have depending on like what the actual situation is, but do understand that we actually try to minimize a type 1 error, creating a type 2 that is not such a big of a deal. Okay, so let's take a look at that. So a television executive believes that at least 99% of households in the US have at least one television. Now, an intern at an executive company is given the task of using a hypothesis test to determine whether the percentage is actually less than 99%. Now, the hypothesis test is completed, and based upon the sample collected, the intern decides to fail to reject the null hypothesis. Now, if in reality 96.7% of households own a television set, was there an actual error made, and if so, what type? So let's just kind of begin by state our null and alternative hypothesis. So again, what was they actually gathering data for? Well, they were gathering data about whether or not the percentage was less than 99%. And again, it was a population that we're referring to, a portion of it. So we're going to use P. So either P was less than 99% or P was greater than or equal to 99%. Okay, so we basically have these two written statements. Now, remind yourself that the hypothesis test failed to reject the null. Okay, so the hypothesis test failed to reject the null. However, in reality, somebody actually got all the data, we'll say, and they got our P to actually equal 0.967. So thus, basically, that seems that the null hypothesis was true to begin with. So since the intern failed to reject the null hypothesis, this is actually what we call a type 2 error. Again, remind yourself that what those two hypotheses actually were, and that kind of will help you guys out there, is that we basically were looking for, was it actually less than this? This was the alternative. And the null was that it was greater than or equal to this. And we basically said that we fail to reject this. And it's always the null when we fail to reject or reject. It's always in reference to the null. Okay? So since we failed to reject this, but we just learned that this is false to begin with, because we just said P actually equals this. So since this is false to begin with, and we failed to reject something that was actually already false, that's where our type 2 error comes in. So let's see about if we can try this other one. So insurance companies commonly use 1,000 miles as their mean number of miles a car is driven per month. Now, one insurance company claims that due to our more mobile society, that the mean is actually more than 1,000 miles per month. And the insurance company is going to test this claim with a hypothesis test and decide to reject the null hypothesis. Now, let's assume that in reality that mean number of cars, miles of cars driven per month is actually 1,250 miles. Was there an error made, and if so, what type? So again, I'm going to read through this and I look for those keywords. And again, we basically we kind of want to claim, and again, those are my keywords. I'm looking for like claim is more than 1,000 miles per month. Okay, so right away, that's kind of giving me my null and alternative hypothesis there. And then, okay, so now that we know that, we also look for, well, what was it true or not? And did we reject it or not? Okay, so begin always by writing what that null and alternative is. So again, that's the first thing I wanted to know about, whether it was more than 1,000 miles. So we have our 2. So mu is more than 1,000 miles. So there's that bottom one is our alternative. That's our research one. And then our mu is less than or equal to 1,000. Now again, remind yourself that basically we said that we have our mu is less than or equal to 1,000 here. This we said we reject. We rejected the null. And again, we always say fail to reject or reject the null. It's always against to the null. Okay? So we reject the null in favor of this one as being the true statement. Okay? Now, in reality, mu was actually equal to 1,250. So was there actually an error made? Well, if we reject this in favor of this, and this is actually the true answer, then isn't 1,250 more than 1,000? Okay, so because the hypothesis was actually false and we actually rejected it, because we had enough evidence to show that it was not, there was enough statistically significant enough evidence to go in favor of the other hypothesis, then technically we made the right decision and no error was made. So let's try this again. A study on the effects of television viewing on children reports that children watch a mean of 4 hours of television per night. Kiko believes that the mean number of hours children in her neighborhood watch television per night is not 4. Now she performs a hypothesis test and rejects the hypothesis. Now assume in reality children in her neighborhood do watch a mean of 4 hours of television per night. Does she make an error, and if so, what type? Okay, so Kiko believes, that's the same as a claim, right? You believe something. So they believe that that mean number of hours is not 4.0. Okay, so that right away, guys, that's my alternative and null hypothesis. We believe it's not 4 hours a night, so there's my alternative hypothesis. And so the opposite of a not equal is an equal. So therefore, my alternative claim is that it just equals 4. Now again, it can be more, it can be less, I don't really know. But I'm just saying that it just doesn't equal 4. When I say not something, it just can be more, it can be less, it's just not that number. Now, as we went through this, the decision was to actually reject the null. Okay, so we reject this null, when in reality, it was actually 4. So when Kiko actually rejected the null, and it was actually true to begin with, we reject something that's true, then we've created a type 1 error. Okay, now that you have kind of practiced to distinguish between a type 1 error and a type 2 error, it is important to note that it's almost every case we would not know the reality of the situation. So those population parameters are usually kind of unknown. We don't really know the actual truth. And we would just have no basis for determining whether something is a type 1 error or a type 2 error until something has actually already been made. Okay? However, knowing what types of errors exist and how they are related to each other, as well as being able to distinguish between them, allows us to interpret decisions in the context of possible realities. Was it actually a good decision to go one way versus another? And these are different things that we ask ourselves as researchers when we do something. Should I do this? And is it actually going to be favorable? Now, is there a possibility that somebody falls in this type of error that could happen? Which error is the worst error to have, type 1 or a type 2? Well, that's going to depend on what exactly you're researching. And that's what we mean by, we normally in the papers interpret this type of stuff and say like, okay, this could happen, but is it really that big of a deal? Is it versus the other one? Is that the bigger deal? Is the type 1 or type 2 error the bigger deal? Okay. Again, please make sure that you are writing down your alternative and null hypothesis. Please make sure that your symbolism that you are using is correct, and make sure you're writing them down, because again, it's really helpful, and we will take all of this and move into the next section and take it another step further.